For the same circuit, okay, let's do a derivation here. So again, we have the same circuits. We have VDD, then we have RD, and we have our NMOS here. Here is VO, which is VDS. And we have two sources, VGS and the voltage that we want to amplify. Both of them is VGS. So yeah, so you can say the DC portion of VGS and the AC portion of VGS. Okay, so the input here is V small GS capital, where VGS is equal to V input plus VGS capital. This is pure DC for the Q point, and this is pure AC, the signal to amplify, the signal to be amplified. So two observations here. Number one, since we want to use the transistor as amplifier, then we are working in saturation region. So to amplify, we must work at the saturation region. Number two, most of the time, since we want to amplify something, this something should be small, right? So we have many cases in which the input is really very small. So in many cases, the input is very small. And that's why it's important to study the characteristics of the circuits if we assume that the input is really very small. And very small means, as we will see later now, maybe in 5 minutes, much less than VGS minus V threshold. So very small means that V input is much less than V input maximum. So it's generally a variable, you know, signal that has maximum and minimum. It's AC. So small means VI maximum is much less than VGS minus V threshold. Okay. So let's see how the circuit will behave under that condition if it's really small, very small. Okay, good. So VO or VDS, V small, DS capital, because now the voltage at the drain source has part of it is DC and part of AC is AC, is equal to VDD minus I small d capital, again because the current now is changing because the input is varying, the VGS is varying, and the ID is small capital, small letter capital subscript, because again there are two signals, AC or two components, one AC and one DC, multiplied by RD or times RD. Okay, and remember we are in saturation, so ID is basically Kn over 2, then V input, which is now two stuff, VI plus VGS minus V threshold square. Usually we call that voltage VGS minus V3, we call it overdrive voltage. So this is called overdrive voltage. V overdrive. But don't worry about the namings, you know. I will just remove this VGS minus V threshold and call it so, just to make our, you know, symbols less, because it's messy now. Okay, so VDS equal to VDD minus RD Kn over 2 And here, this guy is overdrive, so V input plus V overdrive. I'm sorry, overdrive is DC, complete DC. So V overdrive. So everything should be capitalized. Equal to VDD minus RD Kn over 2. And now we're gonna, make this squaring. So Vi square plus V overdrive square plus 2 over V overdrive VO V overdrive. Good. Now, based on the assumption that V input is much less than VGS minus V threshold, that means that Vi square is much less than VGS minus V threshold, which is the overdrive square. And let's give an example. 2 is less than 20. You know, the ratio between them is 1 to 10. Let's now square both sides. So 2 will be 4 and 20 will be 400. Now what is the ratio? The ratio is 1 to 100. Okay, so if something is less than something, then the squaring of that stuff will be much less than the other stuff. Okay, so basically, if we assume again that the input is very small, so we can ignore Vi square plus V over. So this is basically means that Vi square plus V overdrive square is approximately equal to V overdrive square. And we can just neglect Vi square. So let's rewrite now VDS after that assumption. So VDS equal to VDD minus RD Kn over 2. And this will be V overdrive square plus 2 V overdrive, VO V overdrive equal to VDD minus Kn RD over 2 V overdrive square plus, and now I will bring it back to its original shape, VGS minus V threshold square. I just removed VO drive and go back to its original equation, original symbol or term, plus or minus, because Kn will just so RD Kn over 2, and the 2 will go with 2, so we don't need this. V overdrive and VO V, and again V overdrive can be go back to VGS minus V threshold. And now we will have a minute here. So VDS. Let's write this as follows. So VDS, okay, let's write VDS equal to VDD minus KNRD over 2 VGS minus V threshold. So what is Kn over 2 multiplied by VGS minus V threshold? This is basically, if there is no AC input and we only have DC, okay, this will be ID capital. So this is VDD minus RD ID capital. And ID, is the DC portion of ID small, I small d. Remember, we have two components, AC and DC. Minus RD Kn VGS minus V threshold, which is all constant, multiplied by VO. Okay, what is this? This term. This term is basically the DC portion of VDS. So this is VDC. I'm sorry, VDS, V capital, DS capital. So if you don't have AC voltage, the voltage here will be VDD minus ID capital multiplied by RD, and ID is just DC. Okay, minus constant. I will call it GM for some reason now. I'm sorry, constant. Yeah, So constant is RD, which is dependent on the circuit, and another constant here, which I will call GM, and we will see why I call it GM, VO. Good. Remember this voltage VDS, V small, VDS capital, is the AC and DC portion at VDS. So this is equal to, let's call it VO, which is the AC portion, and VD is the DC portion is just VDS. So this go with this. So VO equal to, I'm sorry, this is V input, not this is V input. I am very sorry. V input. Yeah. V input. I just confused this. Okay. VO is equal to so DC is equal to DC. So the AC will be equal to the AC. So GM RD VI. Now, if GM RD is larger than 1, we will have amplification. So we can design our circuit such that the multiplication of Kn VGS minus V threshold by RD is larger than 1. So we will have amplification. So this is number 1. Number 2, VO is out of phase with V input. Again, just like BGT. So BGT amplifier, they were out of phase, and here also they are out of phase. Okay. And as we will see, in the next lecture, this is actually the amplification. So this is EV, the amplification. Or to be more specific, this is EV node. The amplification, assuming that we are not connecting a load, RL. Okay. And now this mysterious term, GM, which is equal to Kn VGS minus V threshold. This is just like GM of the BGT, although of course it has a different equation to be evaluated based on. But it's again the transconductance. So this is the transconductance. So remember, VGM in BGT transistor was VT over IB, or VT, I'm sorry, IC over VT. So here is also our GM. Okay. That's very good. Another and very important observation is that we know that when we have input, and this input is part AC and part DC, we will have output that is also part AC and part DC. Okay, so basically that's what we get, part DC and the part AC. And we know for sure that the DC part come only from the DC part, the DC input, the battery, VGS, V capital, VGS, C capital. Okay. So basically, another assumption that we can do in this analysis is that we can, again, like VGT, solve the AC domain by itself, canceling all DC sources, and solving the DC domain by itself, canceling all AC sources. So the AC and DC domain are decoupled. So DC analysis, we will have DC analysis to determine the Q point, in which we cancel all AC sources. And we will have AC analysis, in which we cancel all DC sources. And actually, this mysterious, transconductance can be derived in another way. So we knew that from BGT that GM is actually, you know, the partial I output over I input. So it was partial IC over or derivative of IC with respect to VBE. Here, it's also partial ID with respect to something in the input, which is VGE, or I'm sorry, VGS. Can we do that? Yeah, we can do it. So we know that, so partial VGS. And what is ID? It is Kn over 2 VGS minus V threshold square. What is the derivative of that? We go, 2 will go in the, we multiplied by Kn 2, so it will be Kn VGS minus V threshold. So another, this is another derivation for it. Okay, we derived it basically first from the circuit analysis, then by the formal definition, and of course both they should merge into the same stuff. Okay, GM usually has multiple forms, and of course all of them are equivalent. So GM till this moment is equal to Kn VGS minus V threshold. It can be written as with many, you know, they can all lead to each other. Yeah, 2ID over VGS minus V threshold. Okay, and also can be equal to the square root of ID 2ID Kn. If you remove ID here and put Kn over 2 VGS minus V threshold square, you will get, you know, the same equation, the first equation. Again, if you remove here this ID and also put Kn over 2, you know, you will again go back to the first equation, this equation here. Okay, so they all lead to each other, you know, but you may find this definition somewhere and this another definition somewhere, so you can just, you know, combine them, or you should know that both are the same, or all are the same. Okay, so the bottom line here is that we can use the transistor to amplify signals. Okay, and we see that there is amplification called the GM-RD, and it's based on this, it's dependent on the circuit parameter like RD and our transistor characteristics and the biasing that we get. So all these parameters can lead, if you choose them right, you can have GM-RD larger than 1, so you can have amplification. For small signals, we can decouple the AC from DC. I mean, we can do the DC analysis by itself, canceling all the AC sources. Then we can do the DC analysis by itself, canceling all the DC sources. Okay, this is number 2. We also get the transconductance parameter. Okay, and it has many forms as we see here. Okay, and of course all of them just lead to the same stuff. Okay, so next time I'm gonna use these observations and these nodes and start to, you know, analyze NMOS or BMOS amplifier circuits. Thank you very much and have a great day. Bye-bye.